Our last lesson for chapter 4, and it's called Numerical Integration. But it's pretty similar to when we did Riemann sums. We used rectangles to approximate the area under the curve. So I've already set this up if you need to pause it and catch up to me. But it said use 4 trapezoids, equal heights, area under the curve of this function from 0 to 2. So A is 0, B is 2, 4. So that formula was b minus a over n. I had that before with the Riemann sums. So 2 minus 0 over 4, which is 1/2. So then I went by 1/2 here from 0 to 2. And then I plugged those into the x squared and got those numbers. And I went ahead and plotted those points on there. So now instead of using rectangles, we're going to use trapezoids. So I'm going to draw. Draw those heights, and then, oh yeah, and I exaggerated the scale on there, so you notice that. So this one's going by 1/4, and this one's going by 1/2, just to stretch those out a little bit and fill up the graph a little bit better. But it does distort the two scales a little bit. Now you can see if we were using rectangles here, we would have all this space up here, and that would be an over approximation. Now here it's harder to tell. It's still an over approximation because there's this little sliver that's going to be underneath each of these. So that side of the trapezoid is going to be above the parabola. But you can see this is a much better approximation than the rectangles because the rectangles gave us all that extra space. Okay. So if we look at these trapezoids, here's, from those of you who had me for honors geometry, I copied this picture out of our geometry notes. When we find the area of a trapezoid, so this is base 1 up here, and this is base 2, and this is the height. Well, that's called the mid-segment of the trapezoid. And if you think about it, it's going to be the average of these two bases. So the area of the trapezoid is the average of the bases times the height. So base 1 times base 2. I usually do it like this, the average of the bases times the height, because when we add the two bases together, if we get an odd number, sometimes I'll take half of the height if the height's even. But that's the average of the bases times the height is the formula for the area of a trapezoid. Okay, so average of the bases. So all the trapezoids have, there are 4 trapezoids there. They're all going to have that 1/2 in them. So the rest of it is just adding the two bases together and multiplying by the height. So this first trapezoid here, it kind of tells you, that's a special trapezoid. It's actually a triangle. But the trapezoid area formula will work for a triangle because we can consider the base 1 to be 0. So it seems kind of weird, but if you think about it, the area of a triangle is 1/2 base times height. And if we treated one of those bases as 0, because it's just a point, then these two formulas would match. So I'm going to put 0 plus, and then that next base here. And a lot of people are used to looking at trapezoids from the side. So you could do that if that made you feel better about your trapezoids, those being the bases on the top and the bottom. But it shouldn't technically matter. So that next one was 1/4. And then the height is going to be 1/2. This is the height of the trapezoid. And it may have occurred to you immediately that all the heights are going to be 1/2. So we could have factored out another 1/2. Either out the back, or we could put it up here and put 1/4. So then that one's going to be plus 1. And then we're going to have 1 plus 9/4. And then we're going to have 9/4 plus 4. Alright, so if we multiply this together, we'd get 1/8. And then if we multiply it by that 1/2, we get 1/16. So that first one is going to be 1/16. Here I'm going to get a common denominator, so that's going to be 4/4. So that's going to be 5/4. So that's going to be 5/16 when we multiply it by this half and this half. Moving to the next one, that's going to be 4/4 as well, so that's going to be 13/4. And that's going to be 13/16. And that last one there, that is going to be 16/4. That's 25/4, which is going to be 25/16. So if we add those together, that's going to be 44/16. And that can be reduced to dividing both of those by 4. So that's going to be 11/4, or 2 3/4, or 2.75, to do a comparison a little later. Okay, so now it's telling us that all the trapezoids had the same height, which we noticed there was a 1/2, and they all had a common base. So we had the 1/2 factored out. We also could have factored out that 1/2. And then what we could notice here is that we have, it's going to get a little bit tricky here, but we have that first base was 0. And then maybe you noticed all of these numbers occurred twice. 1/4 occurred twice, except you can't see that. 1/4 occurred twice, 1 occurred twice, 9/4 occurred twice. So we have 1/4 plus 1 plus 9/4, and then the 4 only occurred once. So we could have done it like that and had 1/2 and 1/2, and the 0 plus the 4 is 4, and that's 10/4, and 4/4 would be 14/4 times 2. I don't know if I'm doing too much there. 14/4. So that's going to be, I'm going to multiply those two together. That's 1/4, and this is going to be 4, and that's going to reduce to 14/2. So this is going to be 8/2, so that's 22/2. (22/2), which reduces to 11, so that's 11/4, which is the same thing we had there. Now that only works if those gaps are equal. Okay, if those gaps aren't equal, then this formula is not going to work. Okay, so if we look at the exact value, the exact value is going to come from the integral from 0 to 2. So that would be, add 1 to the exponent, divide by the new exponent, 0 to 2. 2 cubed is 8, so that's going to be 8/3 minus 0. So that's going to be 8/3, or 2 2/3, which is 2.6 repeating. So you can see that the approximation was 2.75, and this actual value is pretty close, 2.6 repeating. So it says, is the trapezoid larger or smaller? So I was talking about that earlier, those little slivers in between there. So it's larger, the approximation is larger because the graph was concave up, and the trapezoids were above. So you kind of draw, if it's concave up, you're going to get something like that, and this is going to be extra. Okay, so here is kind of a breakdown of the trapezoidal rule. It's b minus a over n, that's the height, And then this 2 here is from the 1/2 that I factored out up there. So the 1 over 2 is the 1/2 I factored out. The b minus a over n is the 1/2 I left inside up there. Then you get base 1 once and the last base once, and all the other bases you get twice. So I actually factored that 2 out, and I put y1 plus y2 plus ... yn minus 1 plus yn. So that's what I did there. All right. So I already got this color coded for us. So the table was created using the temperature, recording the temperature every hour from noon until midnight. Use the trapezoidal rule to approximate the average temperature for the 12-hour period. So they're telling you to use the trapezoidal rule here, but they're also telling you average temperature. So average temperature is an average value. So you should memorize that. Average value is 1 over b minus a times the integral. Okay? So that should be automatic. This is what you associate that with. Now, we're going to take 1, I don't have a function value here. Let's make it up. So 0 to 12, that's going to be 12 minus 0, and that's going to be 0 to 12 of the function of time. Okay. So that's going to be 1/12. And then, if we think about it, we're doing trapezoids, so we're going to have a 1/2. And then all the heights are equal because it's 1 hour. So technically I could factor that out as well. Then we're going to get that first base once plus 2 times. All the bases in the middle will be multiplied by 2. Now, it should be obvious to you, I'm not going to write all these out because I'm going to run out of space. So all the way down here to 65, those will all be times 2, and then 63 will just happen once. All right? So let's see, that's going to be 1/2, and then if we add the 2 single bases together, that's 139, and then 2 times, if we add all those numbers up from 78 to 65, we get 851. Okay. So if we multiply these together, that's going to be 1/24th. And if we add that up, that's 1841. And that turns out to be approximately 76.708. You must go to the thousandths place. Okay. Now for these Riemann sums and for the trapezoids, you must show a sum of products. Oh, and on this, actually, if this was this was a free response AP question, we would box that. And if we're doing the average temperature, it didn't tell us the units on that, so I don't know, degrees Fahrenheit, probably. I mean, obviously, with those numbers. All right. Anyway, so yeah, we would not want to necessarily do all that work down there like that. Okay, so this is really important. So on the AP test, there's going to be one of these 4, and it is one of the easiest things that we do, and yet there's too many students that waste points on this. So we really need to be careful here. So, starting with the trapezoidal rule. The trapezoidal rule has the 1/2 because the average of the bases. It's automatically going to have 1/2 in each trapezoid. Now, these gaps are not equal. So I can't just write out the formula like I did up here, where I just wrote it out like that, because all of those heights were 1. So I could just factor it out right there. I can't do that. So what we need to do here is look at them one at a time. So from 10 to 30, the height is 1. Okay, so the height is 1. So 10 and 30 times 1. Then I'm going to have 30 and 20. And that one's going to be times 2. And then 20 and 40. And that one's going to be times 2 also. And then the last one is going to be 40 and 30, and that's going to be times 1. Okay? Now, this is the AP test, then that's it. That's what you're going to box. I guess I could have highlighted it in the color that it is, blue, except now it's going to look green. Alright. Now, for the midpoint, you're going to take the middle values. So it's going to be 30 and 40. Now the problem that mistake students make here is that if you're taking the midpoint, you're going all the way across here. So your height is going to be 3. And here, your height's going to be 3 also. So you're going to take 3 times 30 plus 3 times 40. Alright? And that's a product, that's a sum of products. Right? Sum of, that's a product, that's a product, sum of products. That has to be shown in your work. Same thing here. We're adding up, and these are products times 2. Okay, so that would be it. If you actually are curious about the actual numbers, this is 165. I shouldn't be boxing those though. This is 210. Alright, so the left Riemann sum, you're going to start on the left. So you're going to have 10, and you're going to multiply that by the height here, which would be 1. Plus, and then you're going to have 30. Oh, I put the parentheses on that. So this is 1, this is 2. Then you're going to have 20, that's times 2. And then the last one is going to be 40, and that's going to be times 1. And you don't use that last 30. That's it. That's going to be 150. Dang it, I keep boxing those. If you box both of those, they're going to grade it. The whole point of not boxing this is in case we make a mistake. Okay. So we don't want them to take points off if we make an arithmetic mistake. Pretty sure that underlining would kind of count as a box also, but alright. So now right Riemann sum, that just means we're gonna take the 4 numbers on the right instead of the 4 numbers on the left. So how do I want to show this? So the left Riemann sum was these 4 right here. And the right Riemann sum is going to be these 4 on this side. Okay? So the gap is still, so the gap here is 1 times 30. So that's going to be 1 times 30 plus 2 times 20 plus 2 times 40 plus 1 times 30. Alright? And that one turns out to be 180. Okay. Now, I want to go back and use this as an example of how to use the fundamental theorem of calculus. So they're telling us that f of 7 is negative 15. What's the value of f of 1? So what we can do there is we can look at the integral from 1 to 7 of this function. Okay, and then that would be f of 7 minus f of 1, because if we integrate a derivative, we just get the function back. Okay, so if we look, it tells us that f of 7 is negative 15. So if we're solving for f of 1, we could add f of 1 to the other side over there. So f of 1 is going to equal f of 7, which is negative 15, minus this integral. Now, this integral, we approximated it 4 different ways up here. So we could use any of these numbers. They're not going to ask you all 4 of these on a test. They're going to ask you one of them. I just demonstrated how all 4 of them can come off the same table. So let's use this as an approximation of that integral. Okay, right here. This is an approximation for that from 1 to 7. So that value is 165. So if we subtract that, that's going to be negative 180. Okay, and still even we would box this over here. All right, so that wraps up first semester. Congratulations, first semester calculus. It's about that time. Have a good day.